morning, good afternoon, good evening, whatever the case may be. We are back and we are better than ever. Let's go indeed. The great tune by the legendary rock band The Cars. We are talking about the greatest aunties of all time today. For example, see how many you can guess here. This is the great Aunt B from the Andy Griffith Show. Of course, who can forget who is this from the Fresh Prince of Bel-Air? There you go. There's Auntie Viv. Auntie Viv. And then you guys are probably a bit too young for this from Sanford and Son. Auntie Esther. There she is right there. Oh my goodness. Who can forget Auntie Edna from the classic film Vacation? There she is stuck in the car after Clark's famous jump. Oh, you all know this one from Harry Potter. That is Auntie Petunia. And then, of course, we have Auntie Marge. Remember what happened to Auntie Marge? She didn't study her calculus. That's why that happened to her. Oh, my goodness. Do you remember this one? Auntie May. Auntie May from Spider-Man. Oh, that's sort of strange. A pretzel? Oh, Auntie Anne's pretzels. There you go. And finally, the greatest aunt. Well, one of the greatest aunts. Not the greatest aunt, but one of the greatest aunties of all time. Auntie M from The Wizard of Oz. But without question, the greatest auntie of all time in the entire universe is capital F of X. Capital F of X. Why, you might ask? Well, boys and girls, this is antiderivative with a slight spelling change. This is antiderivative. Capital F of X. And we shall get to that in 1 second. Okay. Oh, ooh, who's that? That's the lesser known and quite creepy uncle derivative. Just let that sink in for a second. All right, let's move forwards. Antiderivatives, here we go after the comedy show. There's a lot of problems in calculus where we know the rate of change with respect to another, but we don't have a formula which relates the variable. In other words, we know the derivative, but we need to know the original function. For example, if we know that the derivative of the gradient function, the tangent function, is 2x plus 3, what is the original function? If we know the rate of change in a temperature, what is the temperature function? If we have a function that gives us the rate of change in a temperature, what is the original function? In the process of finding that original function from the derivative, that is, finding f of x given its derivative, is the reverse process of differentiation, and we call it anti-differentiation. Okay, so here we go. Let us consider the derivative. dy dx equals x squared. Now make sure you understand what we're asking or what I'm saying here. This is the derivative, so I'm asking you, what is the original function? What did we take the derivative of in order to get x squared? Or asked another way, what is y in terms of x? Okay, so we know from our power rule that this must involve x cubed, right? Because if we take the derivative of x cubed, we subtract 1 and we end up with x squared. But let's just say I had g equals x cubed. Well, g prime equals 3x squared. Well, we need it to be x squared. How do we do that? Well, you have to ask yourself, or one way to do it is, okay, the derivative of x cubed is 3x squared, so the 3 is coming down to multiply the x squared. What could we have as a coefficient of x cubed in order to end up with x squared after we multiply by 3? And that answer would be 1/3. So the original function here is y equals 1/3 x cubed. Let's test it out. Y prime equals 3 times 1/3 x, or I should say dy dx here, because that's the notation they used here. Dy dx is equal to 3 times 1/3 x squared, and 3 times 1/3 is 1, or x squared. So y equals 1/3 x cubed plus 3. It's also important to note that I could have any constant out here, like plus, I don't know, 8 or 82 or 829 or 8.29, doesn't matter. Any of these would work. So what we say is it is the simplest function. The antiderivative is the simplest function where we can end up with the original function. So we all know that there could be a constant here, but we say that the antiderivative is the simplest of the infinite number of functions. Okay? And we'll do a lot more examples, or a few more examples here in a second. So, formally defined, if capital F of x is a function where its derivative equals lowercase f of x, we say the following. Of course, the derivative of capital F of x is f of x. And here's the important part. If this is true, then if this is true right here, if the derivative of capital F of x is equal to f of x, then the antiderivative of f of x is capital F of x. Hence the capital F, the greatest, being the greatest anti of all time, the antiderivative, not the creepy uncle derivative. So here are the examples we're going to use. So we have A, okay? So find the antiderivative of x cubed. Well, I'm going to go ahead and just say, okay, I know that y prime equals x cubed. What is y? Well, y is going to have to equal something to the 4th power, because the only way that I'm going to get a cube after I take the derivative of something is by subtracting 1 from 4. So it has to be to the 4th power. But look here, the coefficient must be 1, okay? So if I take the derivative of this, I'm going to multiply by 4. So I have to ask myself, 4 times what is going to give me 1? Well, clearly that's 1/4. And maybe you see a little pattern here. So I'm going to do something else here. Let's say we had y prime equals x to the 5th. I will tell you very quickly that y equals 1/6 x to the 6th. AII, if, I don't know, y prime equals x to the 10th. Hopefully you're seeing a pattern here. Well, y would be 1/11th x to the 11th, right? Because if I take the derivative, 11 times 1/11 is 1, subtract 1, and I get 10. So this is the antiderivative of x to the 10th, okay? And there's just a little quick formula here. If I know that y prime equals ax to the n, in all of these cases my a was equal to 1, but it doesn't matter. It doesn't matter what the coefficient is. This will work. Then the antiderivative is equal to x to the n plus 1, or a x to the n plus 1, divided by n plus 1. Divided by n plus 1. Think about that. So let's use this one. 10, the antiderivative, I added 1, and then I divided by 11. I divided by that result. I could also write this obviously as, hopefully obviously, as x to the 11th over 11. Okay? Let that sink in. Pause if you need to, but go ahead and let that sink in. With that in mind, I'm going to skip and do example C before I do B, because that falls right into line here. Okay, so with example C here, I'm going to write that as y equals 1 over root x. Actually, that's the derivative, because I'm going to find the antiderivative. Or y equals x to the negative 1/2. Okay, or y prime, sorry, I keep messing that up. So the antiderivative of y, in other words, what function that I take the derivative of, will I end up with x to the negative 1/2? Well, this is a power function, so I can use this little rule here. So I'm going to add 1 to 1/2, okay? So that would be negative 1/2 plus 1 is a positive 1/2. And then I'm going to divide the entire thing by 1/2, or divide the a here. In this case, a is 1 by 1/2. And so that would equal 2x to the 1/2. Yes? Okay. Don't believe me? Take the derivative. See if you get x to the negative 1/2. 1/2 times 2 is 1, the coefficient. And 1/2 minus 1 is negative 1/2. So you get x to the negative 1/2, which of course is equivalent to 1 over root x. Okay, last example here, I'll do b. So I have, I'll write it differently this time, I have dy dx equals e to the 2x. So you got to think a little bit here. You know that the derivative of e to the anything, I'm just going to put a box here, if y equals e to the anything, its derivative is equal to e to that anything times the derivative of the anything. Yes? Okay. So we have to ask ourselves, what am I going to take the derivative of and end up with e to the 2x? Well, you know that e to the 2x must be involved. Okay, because the derivative of e to the anything is e to the anything. So I know that's involved, right? Okay. So then, if I take the derivative of this, remember, I'm trying to take the derivative of this and end up here. If I take the derivative of this, I have to multiply by the derivative of 2x. So that would be times 2, right? But I can't have a 2 in front, I need a 1 in front. So I need something in front of here that compensates for multiplying by 2. And that would be 1/2. Now I'm going to erase this 2 here. Okay. So the antiderivative of e to the 2x, oh, I don't know why I have y prime here, this is y, sorry about that, is 1/2 e to the 2x. And if you don't believe me, let's take the derivative. Y prime equals 1/2. The derivative of e to the 2x is e to the 2x. And up here I wrote dy dx, so I'll rewrite it again just so there's no confusion. So I started with y, and I'm taking the derivative of y with respect to x of 1/2 e to the 2x. So that's 1/2 e to the 2x times the derivative of 2x, right? 1/2 times 2 is 1, and I get e to the 2x. So I have proven that the antiderivative of e to the 2x is equal to 1/2 e to the 2x. Okay, until next time. See ya!